morning and a very warm welcome to you viewers in this second lecture of mine on Cooper pairs. To begin with, I would like to thank you all for your fairly good response to my first video, and that indeed would help me keep myself actively engaged in this pursuit of mine to disseminate and share knowledge with you. Now, before I pick up things from where I left in my last lecture, I would rather like to recapitulate certain important points from there. First of all, we had seen how the motion of an electron through a solid was able to deform the lattice, and how that lattice deformation was able to communicate sort of attractive interaction between a pair of electrons. And from there, we were able to calculate the approximate size of a Cooper pair. Then we had seen how this attractive interaction between a pair of electrons can be visualized as an exchange of virtual phonon between them. A phonon is an elementary excitation in the quantum mechanical treatment of lattice vibrations. However, in this case, the phonon is a virtual phonon, and the phonon is virtual because an electron cannot undergo a sufficient change in energy at very low temperatures to create a real phonon of short wavelength. So a virtual phonon in this process is emitted by one of the electrons and absorbed by the other within such a short period of time, which is less than 1 by omega d, that its existence is allowed only by the energy time uncertainty relation. Now momentum is conserved in the individual emission and absorption processes, but the energy is conserved only overall. In this particular figure, I have tried to sketch the phonon exchange process. So this is our first electron with wave vector k1 coming from this side. It emits a phonon and gets scattered in this direction, and its wave vector changes from k1 to k1 prime. Now the other electron coming from this side with the original wave vector k2 captures this phonon and gets scattered in this direction with the new wave vector k2 prime. So its wave vector has changed from k2 to k2 prime. Next, we had seen how the RedGreen experiment, which is also known as a thought experiment, is performed by switching an interaction between these two electrons which are just above the Fermi surface. So we pick two electrons in states just above the Fermi surface and sort of switch an attractive interaction between them. So these two electrons, they have got the wave vector k1 and k2 respectively, and E1, k1, E2, k2 shows their energy values. Mind you, these two electrons, they are in states just above the Fermi surface, because the available states above the Fermi surface only lie in an energy thickness of h cross omega d above the Fermi surface. Now, you know, all the states below this Fermi surface, they are completely occupied by electrons which are fermions, according to the Pauli's exclusion principle. Now, we also had seen, for our purpose, it was sufficient to consider k1 is equal to minus k2 is equal to kc. So for our purpose, it was sufficient to consider the electrons where with k1 is equal to minus k2. Now, the associated two-particle wave function psi r1 r2 must obey the Schrodinger equation. So I write the associated two-particle wave function psi R1 R2 must obey the Schrodinger equation and I'm writing down the Schrodinger equation minus h cross squared by 2m del 1 square plus del 2 square psi R1 R2 plus V R1 R2 psi R1 R2 is equal to E psi R1 R2, and this is equal to small e plus 2e f naught psi R1 R2. So this I give equation number 2. Now here the small e is the energy of the electron pair relative to the interaction free state. So we write where small e is the energy of the electron pair relative to the interaction free state. So there this interaction free state में V will be 0, in which each of the two electrons, each of the two electrons would possess an energy EF naught is equal to h cross square kf square divided by 2m. Now the wave function of the two electrons can be expanded as a linear combination of plane waves. Now the wave function of the two electrons can be expanded as a linear combination of plane waves. I will tell you just a little later why plane waves, as psi R1 R2 is equal to K1 K2 F K1 K2 e raised to the power I K1 dot R1 into e raised to the power I K2 dot R2. So this is equation number 3. Now Cooper looked for states of this form with an energy less than 2 EF naught being the energy of two normal electrons at Fermi surface. Such states would correspond to bound states of two electrons, and their existence would indicate that the normal state, as represented by the Fermi sphere, was unstable against the formation of the bound pair of electrons. Now, for the lowest energy, the center of mass of the two electrons is at rest, and this is achieved by including only states with equal and opposite momentum. So, I can also write it out. For the lowest energy, the center of mass of the two electrons is at rest, and this is achieved by including only states with equal and opposite momentum. K1 is equal to minus K2 is equal to K. In the expansion of equation 3. So, for the lowest energy, the center of mass of the two electrons is at rest, and this is achieved by including only states with equal and opposite momentum. K1 is equal to minus K2 is equal to K in the expansion of equation 3. It then simplifies to, means equation 3 then simplifies to equation 3 then simplifies to, I'm writing psi R1 R2 is equal to 1 upon L cube whole square summation K GK e raised to the power I K dot R1 minus R2. This I take as equation number 4. Now, where the summation is restricted to states K just above the Fermi surface to the region H cross omega d, because of the fact that the available energy states of the Fermi surface lie in an energy thickness of H cross omega d. So I can write it over here, where the summation is restricted to states K, this is small k, states K just above the Fermi surface, and to the region H cross omega d, and therefore we can write this H cross square K square by 2m, this will lie within these two limits, EF naught plus H cross omega d and EF naught, quite obviously. So this I write as equation number 5. Now, the quantity Gk is involved in this equation number 4. So the quantity modulus of gk square is the probability of finding one electron, in state k and the other in state minus k, and the other in state minus k. Now, if we look into the condition 5, means equation 5, together with the Pauli's principle, then that will give us, so due to Pauli principle and the condition 5, we get this. We have gk is equal to 0 for k, either k less than kf. This kf is the Fermi radius in reciprocal space, or k greater than 2m.E.F. naught plus h cross omega d whole divided by h cross square. So this we directly get by looking into condition 5 in the light of Pauli's principle. So now this I give equation number 6. This is equation number 6. Next, now you have to keep track with the equations, viewers, because it's very important. We are doing the mathematics, so keeping track with the equation numbers is very important. So now what we do, we insert equation 4 into equation 2 and then multiply by e raised to the power minus ikr and finally integrate over the normalization volume. So I'm writing it. What we do, so we insert 4 in equation 2, then multiply by e raised to the power I k dot r minus I k dot r, multiply by e raised to the power minus I k r, and then integrate over the normalization volume, and it will yield h cross square k square by m gk plus 1 upon L cube summation k prime gk prime v kk prime is equal to small e plus 2 ef naught gk. This I give equation number 7. So I repeat it once again. By inserting equation 4 into equation 2 and then multiplying by e raised to the power minus ikr and then finally integrating over the normalization volume, we get h cross square k square divided by m into gk plus 1 by L square, summation going over k prime values, gk prime v kk prime is equal to small e plus 2 ef naught gk, where the interaction matrix element vkk prime, where the interaction matrix element vkk prime v kk prime is equal to integral Vr e raised to the power minus I k minus k prime dot r dr. This is equation number 8. So this is the interaction matrix element. It's given by Vkk prime, that's integration Vr e raised to the power minus I k minus k prime dot r dr. Now this interaction matrix element describes the scattering of electron pair k minus k to k prime minus k prime and vice versa. So I write it out. The interaction matrix element V k prime describes the scattering of electron pair, the scattering of electron pair which pair? This pair k minus k prime to k prime minus k prime and vice versa. Now, in the simplest model, this matrix element is assumed to be independent of K and attractive. So, in the simplest model, this matrix element V kk prime is assumed to be independent of K and attractive. That is V kk prime is less than 0, so that is negative. So we can write V kk prime, this is equal to minus V naught. V naught is positive for, this is minus V naught for h cross square k square by 2m h cross square k prime square by 2m to be less than EF naught plus h cross omega d. That means h cross square k square by 2m, h cross square k prime square by 2m, these two energy values associated with the two electrons with wave vectors k and k prime must be greater than EF naught, that is the Fermi energy, and less than EF naught plus h cross omega d, otherwise 0. So 0, otherwise, so you can see now V kk prime is equal to minus V naught greater than 0 for these two energy values of the two electrons in states k and k prime must be greater than EF naught and less than, means they must be lying between these two energy values, means this is greater than EF naught and this is less than EF naught plus h cross omega d. As I have been telling you continuously, that the available states above the Fermi surface, they lie in an energy thickness of h cross omega d. Now this I take as equation number 9. So hopefully you are keeping track with the equations. Then let us have a look at equation number 7. So it now follows straight from equation 7. So it thus follows from equation 7 that minus h cross square k square by m plus small e plus 2 ef naught gk is equal to, say, minus a, where I will give you the value of a. This is equation number 10, where a is equal to so let me show you equation number 10 again. This follows from equation number 7. So this is equation number 10. So where a is equal to v naught upon L cube summation going over all values of k prime gk prime. So this I write as equation number 11. Now a is independent of k. Now if we sum equation 10 over k values and compare with equation 11, then to maintain the consistency, what we can do. So let us try to see. So now if we sum equation 10 over k values over k and compare with equation 11, then the consistency demands that what it will demand, you can work it out yourself, v naught divided by L cube k1 divided by minus e plus h cross square k square by m minus 2ef naught. So this I take as equation number 12. Now what we will do, we will replace the sum over k by the integral over k. So we replace the sum over k by the integral. So what we are doing, we are replacing this sum over k by the integral 1 by 2 pi cube dk. So the sum over k values is being replaced by this integral, and you might have seen already such summations in the context of exchange interaction between electrons. So if you recall, this kind of replacement of summation into integral you might have encountered while doing exchange interaction between electrons. Now what we will do next, we will now split the integral over the entire k space into an integral over the Fermi sphere and the energy. Okay? So next, now we split the integral over the entire k space over the entire k space into integral over the Fermi sphere, the Fermi sphere, and the energy, and we can obtain from equation 12, and obtain from 12 1 is equal to V naught 1 by 2 pi cube dSE by mod of grad E, means gradient of E, K dE divided by 2E minus small e minus 2EF naught, where E is equal to h cross square k square by 2m. So you can see this. Now where the volume element, where the volume element dk is separated into an area dSE on the energy surface, on the energy surface, and a component dk perpendicular normal to the surface, normal to the surface, that is, as I had mentioned you earlier, that is, this dk we can write as the product of dSE and dk perpendicular, and dE is equal to gradient E dk perpendicular. This is quite obvious. This gradient E, k means rate of change of E as k changes, and k changes normal to the energy surface. Therefore, this is dk perpendicular. That is, dk perpendicular is equal to dE divided by gradient E. And therefore, now you can understand this particular equation. Next, now I just forgot to put the equation number here. This equation I provide equation number 14 to this. Now we perform the integration. That means we take up equation 14 and perform the integration. I show this equation once again. Now we are performing the integration over this equation 14. So by performing we obtain, you can also practice it, try it at home, this you will get. So by performing the integration, we obtain 1 is equal to, what do we obtain? 1 is equal to V naught Z EF naught plus H cross omega d, these are the two limits, dE divided by 2E minus small e minus 2E F naught. So This is equation number 17. E is nearly equal to minus 2h cos omega d e raised to the power minus 2 by v naught z e f naught. For this I have put equation number 17. That means this small a is less than 0. That means it is negative. Here we get the negative value. So now this also brings our discussion towards an end, because this is an all important result. It clearly shows that there exists a 2 electron bound state whose energy is lower than that of the fully occupied Fermi C by an amount small e, given by E minus 2 EF naught. That means the ground state of the non-interacting Fermi electron gas becomes unstable when a minute attractive interaction between electrons is switched on. So with this, we come towards the end of our discussion on Cooper pairs. So viewers, after having a long mathematical session with you, now I would like to conclude this lecture with the following takeaways. Number 1, the ground state of the non-interacting free electron gas becomes unstable when a minute attractive interaction between electrons is switched on. Number 2, this instability leads to the formation of 2 electron bound state whose energy is lower than that of the fully occupied Fermi C. Number 3, in reality this instability leads to the formation of high density of such electron pairs, so-called Cooper pairs, via which the system tries to achieve a new lower energy ground state. Last but not the least, the wave function that we have taken up in our discussion has got the spin part also, so that the total wave function is antisymmetric in nature because the electrons are fermions, and therefore we can say that the Cooper pair is comprised of two electrons of equal and opposite wave vectors and opposite spins. With this I conclude my lecture, viewers. Goodbye. Have a nice day.